let's get started on just a little recap of where we were at. It's been a little while. We'll get caught up fast, so be ready for that. So no, there is new stuff here. I'm just not going to write new stuff. I already have it here. So this is what we left off on, finding eigenvalues and eigenvectors. So I wanted you to try this one. And then I think I posted this so you can see all that. Okay, so that's where we're at. So you need to know, that'll be an obvious one to do, that you'll be able to calculate. And then I think I threw up this one. This theorem is new. And this, when you calculate this, you get irrational eigenvalues. So that's a possibility. So something can be irrational. Most of the time we won't work with irrationals, but just an FYI. Okay, theorem 5.1 are properties of eigenvalues and eigenvectors. You can go through that more detailed explanation on page 297. I use this little arrow just for corresponds to, because there's a lot of verbiage in here. So this is what it says. Let A be an n by n matrix, and we'll have lambda correspond to V. So if lambda corresponds to V of the matrix A, then lambda to the k corresponding to the eigenvector V of A to the k. So if you're raising k to a power, you end up getting lambda to a power. Okay, so that's a property of eigenvalues and eigenvectors. Another interesting one is if A inverse exists, then the eigenvalue is 1 over A, given this original statement for eigenvalues and eigenvectors. The other one is interesting, and I do go through a little bit of the proof later, or at least one similar. If you have a set of eigenvectors, each one of these corresponding to the eigenvalue, right? And you add 0, the 0 vector, then that is a subspace of n space. So it stays in the set. You can show closure. The proofs of those are 27 through 29. I don't think I assign those, but you can take a look at those and see how they're done. I think I do a couple, or at least I highlight a couple later is my plan. Okay, then going on to 5.2. Oh yeah, and I'm going to try to do this in portrait mode instead of landscape. Maybe we can get more on the page to explain things. The videos I think look pretty good, so I did this already in Calc 3. So next definition, 5.2. All right, so let T be a linear transformation, and goes from V to V, where V is a vector space. Lambda is an eigenvalue of T if there is a non-zero vector V in V such that T of V equals lambda V. So that's like the matrix definition, but it's a linear transformation. V is an eigenvector of the linear transformation T corresponding to lambda. So it's defining a linear eigenvalues and eigenvectors with a linear transformation, kind of a more general way of describing the transformation. Okay, so we'll look at this and some examples in a bit later. I highlighted one example in the book, example 7, and it says find lambda and V for the transformation, the linear transformation T from R3 to R3, and basically wants you to find it. So I didn't work it out, so I want you to look at that as an example to work out. So with this form, so this is what the transformation is, right? It's basically a polynomial, well, not really a polynomial, but it's taking the coordinates and you're adding and multiplying by a number. So it's just transforming it somehow. So you can create the matrix using those values to do the transformation. So if you can see, here's the first vector. So that's just 1, 0, 0. This is the second vector, -8, 4, -6. And the third vector, 8, 1, and 9, like that. So it's basically V1, V2, and V3. So then, take a look at this. If you work it out, see, so, and then go back to example 6 to find the eigenvalues and eigenvectors of the transformation of A. Once you do that, you'll see that these are the vectors. And then we'll see that you can do the product and get your transformation. So say that's equal to, and then you want this to have basically the form of lambda x. Right, so it's going to be a product of your matrix times lambda. Okay, so check that out in the text. Okay, just moving on. So it's all there. You can look at it yourself. So let's go on. Let's see. I did another couple examples here that I worked out. Let's take a look at this one first. So this is example 18, or number 18 in the book, page 300 in 5.1. I'll try and do a few homework problems, a few more as we go. So the statement is find eigenvalues and eigenvectors for the linear transformation. So this is what's given, okay? And so you can create the matrix A, and you can see that this product is that vector, right? Ends up being a 2 by 1, which is this vector. So look at that. Okay, so then set up your characteristic polynomial. Okay, so you do your matrix product, you get your polynomial, set equals 0 and solve, and you'll get lambda 0, lambda 2. So try that. So pause that and try that. And then substitute back for your lambdas to find your vectors. So kind of pause it and try it on your own for a little recap, little review of stuff. Okay, then example 24 has to do with the subspace stuff. Okay, so example number 24 says V is a linear transformation, or T is a linear transformation from V to V. Lambda is in R. Prove that W, V and V, such that T of V is lambda V, is a subspace of V. Basically, it's saying those eigenvectors are a subspace with this linear transformation. So think about how you would prove that. Okay, so maybe pause that and think about how you might do it. And I really didn't want to spend too much time on this and get on to the new stuff, but okay, so you want to show closure of both addition, scalar multiplication, and that it's non-empty, meaning 0 is in it. Okay, so try that. Go ahead and erase it. So first, I show that 0. Oops, I didn't mean to erase it. I actually did erase it. First, show that 0 is there. Okay, so you put in 0. Of course, you're going to get 0. So it's non-empty. This is the empty set. So W is not equal to the empty set. Then I choose two vectors in W and show that the sum, looks like I need to close that, is equal to that. So that's true just by that T is a linear transformation. But if you rewrite it in this form, then that is a vector in this set. So V is in here such that this is true. So so this equals lambda T, or I'm sorry, let me be back here. So T of V1, V2 equals lambda times the vector. So this vector behaves just like this, so it makes sense. So therefore, you don't really need this step here. I just put that in. So therefore, V1 plus V2 is in W. Now you got to show closure for R. I can go ahead and erase this part right here. Okay, so R is an R. and then you show this product, basically you can just commute that. That is still another vector. So basically back here, RV1 behaves just like this, where you get lambda RV1. And so it's in here. So it's closed under scalar multiplication. Therefore, W is a subspace. So 24 is really the more general case to show that the eigenvectors are a subspace as well. But in that case, though, you have to throw in 0. This one, you automatically get 0 because it's a linear transformation. Okay, so again, take a look at those homework sets. Okay, then this is where we'll start the next lecture video. This is, we're going on to 5.2 on diagonalization of matrix. And so we're just doing 5.1, 5.2. And then we're actually going to go on to chapter 9. We're going to skip the other stuff and go right to chapter 9. I'll talk about that later. Don't worry about it now. And that'll be it. It's a lot, but that'll be it. Okay, so this is one of the major theorems that's this concept of diagonalizing a matrix. So you take a matrix, and essentially it's like factoring it. So it's like you're factoring the matrix into more simple forms of matrices so that you can operate on the matrix much more easily. And so this is the first steps in that discussion, basically. So let A be an n-by-n matrix, lambda 1 through lambda n be in the complex plane, right? So those are complex numbers. And V1 through Vn are the non-zero vectors in n-space, and they're corresponding vectors. I'm not sure I said that, but they're corresponding. Let C be the n-by-n matrix, having V sub j as the jth column vectors. So I wrote it actually down here. So C is these column vectors. So these are the vectors for C. Then let D be the diagonal matrix, where you have lambdas on the diagonal, right? Those that are given. And then zeros elsewhere. That's like a large, you just don't put them in, that's a large 0. So this is a diagonal matrix. So you're defining D and C. Then you have this statement. Then A times C is equal to C times D if and only if lambda 1 through lambda n are eigenvalues of A and V sub j are the eigenvectors of A corresponding to the lambdas. So it's just a lot of words just saying what I just said earlier. They correspond. So the eigenvectors correspond to the lambdas. Okay, that being the case, it's basically saying that's how you can write this form AC equals CD if and only if those are the eigenvalues and the corresponding eigenvectors. So the proof is really just about expanding out that form and seeing how it works. So take a moment to look at that and see if you can maybe start the proof, but we are going to go through the whole thing.